Welcome to our advanced machine learning lecture, and welcome here to this chapter on imbalanced learning and specifically cost curves. This is the second part of cost curves. So in the first part, we already introduced the concept of cost curves simply with respect to misclassification errors. So here we will take a look at cost curves based on true cost matrices. We'll discuss how we can compare classifiers with this and then kind of wrap up with a comparison to ROC, which we already did to a certain extent in the first part. So, well, we will now assume that misclassification costs are not equal, so again we are in a binary classification scenario with a positive and a negative class, or a class +1 and a class 0. I guess I will usually here write this as +1 and 0 in the slides. And now we simply assume that the costs of producing a false negative are not the same as the cost of producing a false positive, because, as I've said before, otherwise we'll simply add up with a scaled version of the regular misclassification error, and that's not really cost sensitive. So what we can now do is we can, as before, develop a little formula for our expected costs based on this pi plus setting of the prior probability for the positive class. So when we did this for the misclassification error, we had this pi plus times the false negative rate and 1 minus pi plus times the false positive rate. And now these two cases we simply have to multiply with their associated costs. So maybe let's do the positive case. So we sample a positive element, we produce an error that happens with the probability of the false negative rate, right? That's probability of producing a negative label, although it's truly is positive. And now we simply multiply that with the associated costs. We do this also for the case where we sample a negative label, and then the sum of these two terms gives us pretty obviously the expected costs as a function based on the prior probability pi plus. So the first thing we could do is we can kind of consider what are the maximal costs that we could incur from that formula, and I guess that happens when we have a classifier that mislabels everything. So when the false positive rate and the false negative rate are both 1. So that's kind of the worst case that can happen. I guess one could go into debating whether we could consider a different setting, because that's kind of a perfect classifier if we would swap around the labels. But formally it's the worst thing that can happen. And we now can calculate the maximal costs that we could incur, and simply now insert a 1 for FPR, insert a 1 for FNR. We don't even really need to resort terms a bit. This here gives you the maximal costs that can happen. Again, as a function based on pi plus. And what we can now do is we can simply consider normalized costs. So normalized costs are simply, it's still this formula here that we developed here in the beginning. The only thing is we will now divide everything by this guy, okay? To have these normalized costs as a metric between 0 and 1. So 0 would be no errors, 1 would be, well, we basically have this terrible classifier that mislabels everything, which gives rise to this slightly more complicated formula, and I will not now read this out. It's pretty easy to see that we can distribute this now into two parts. So one is this blue part and one is this red part. And what you can see there is that, so we have our blue part, which is like a term times the FNR, and we have this red part, which is a term times the FPR. So what I now want to do is I want to simply introduce a little abbreviation. So I want to introduce a symbol for probability times cost. So probability times costs is simply this pi plus times cost of Fn. Okay, so this is basically, let me maybe now remove a lot of these different scribblings. So I just want to introduce an abbreviation for this product here. So pi plus times cost Fn. So this is this prior probability times the cost. And I will now also call PC plus, so this probability times cost, will not really take this as an abbreviation of pi plus times cost Fn, but of its normalized version. So this we can see here. And the next insight is now that if we look at this reddish guy, this is exactly the same as 1 minus PC plus. This is really easy to check. I guess we can do this in our head because these two guys here are the same anyway. And if we do 1 minus PC plus, so what do we have to do is, I guess we have to take this blue guy here and then take this guy and subtract this guy, so these two guys will cancel out, and what remains is exactly what we need. Nice. So this also does check out. So what we now want to do is we kind of want to go back to this nice little structure that we already saw for cost lines in the previous section. So what we want is we want a function of our, so we want to express our normalized costs now as a function where PC plus is the input argument. So we want to plot this in terms of PC plus and arrive at a cost line where the slope is again FNR minus FPR and where the intercept is FPR. And we can check that and take a look at this, whether this works out. And well, I guess it does, right? Because we constructed it in such a manner. So if we look at that, it really nicely checks out. I guess you can, do we actually need to do anything for this? Well, no. This is PC plus times FNR, and that is, yeah, well, I guess we have to rearrange terms a little bit, right? So insert this. Well, I guess we did this for you. So we have, here we have PC plus times FNR, and here we have 1 minus PC plus times FPR, which is exactly what we have here, okay? And now we just reorder terms ever so slightly, so we just collect everything that belongs to PC plus, because this is a function in terms of PC plus, this is our slope, and this is our intercept. So this is the regular form that we also had before in the first plot for cost curves based on the misclassification error. So we now have exactly the same duality. We can go from hard label points in rock space to these cost lines and back again. The only difference is now we plot this in this PC plus thing in terms of this probability cost. So axes have changed their meanings. So here it's PC plus, and here it's normalized expected costs, I guess. Especially the y-axis we have strived for anyway. We can now again generate for a given ROC curve or for a classifier, for a probabilistic classifier with different square thresholds, this lower envelope that works exactly as before. And we can now also kind of visually analyze this a little bit. So if our cost curves lies here on this line of these trivial constant classifiers, I guess we don't like that because we haven't really reached anything. So we could reach that performance by producing a trivial system that spits out constant values without even considering the features. But if we begin to kind of lie below this line, below this triangle here of these two trivial classifiers, we find that interesting. So this region here, this range, we usually call the operating range. So here, this is roughly 0.14 to 0.85, and this is the interesting range where our probabilistic classifier works better than a trivial system. We can also begin to compare cost curves of different classifiers. I guess that is what we wanted to do anyway. So pretty obviously, if at a given PC plus value, classifier C1's expected costs are lower than what C2 does, exactly at the same PC plus point, then C1 outperforms C2 at that operating point. Seems pretty clear. If one cost curve is completely below the other, we would say that this associated classifier completely dominates the one that we are comparing to, and in general, very often these cost curves might cross, which indicates that our classifier C1 outperforms C2 for a certain operating range, and vice versa. We've shown you another example here. We have one like operating range here and one operating range here, left and right hand side of this intersection point. And the vertical distance between the two cost curves of C1 and C2 at any of these PC plus values now directly indicates the performance difference between them at that operating point. This is also pretty nice. I guess that's it. Guess I didn't say too much now about the comparison between our C curves and cost curves. I guess we already did that pretty nicely in the first part, and you should now have a reasonably understanding, better than a feeling, on how to construct these curves and how to use them in practice and what to read off of them in a practical application.